Okay, folks. It's that time of the morning, so I'm going to go ahead and get started. I'll start by passing the sign-in sheet around. Remember, so that we don't have any issues, it goes all the way back and then all the way forward. Okay, the very first thing I want to do is just make a couple of quick announcements. The first announcement is that as of yesterday, I, per the request of the university, uploaded for all those they requested information about. I uploaded where you stand in the class. When I do so, one of the prompts asks, is the student at risk or is the student not at risk? I wanted to let you know that for any student that currently stands with a D or F average, I go ahead and say at risk of failing. The reason I do that is because you have to have a C or better in this class to go on to the next chemistry course. So College Chem 2. And so for me, that means that it is at risk of failing and having to repeat the course. So it is a D or an F. Now, with respect to that D or F, you have to keep in mind that the exam grade that I'm about to pass back is 130 points out of 190, I think it was. So it's a significant portion of the grade. The other thing I want you to keep in mind is that as I pass back this exam, and as you receive, if you're at risk, as you receive the notification from the university, it doesn't mean that you cannot pull a good grade in this course. Because I do drop your lowest exam grade. I drop lowest homework grades. I drop lowest quiz grades. I don't know how many, you would have to look at the syllabus, but I dropped several grades. So it means that you can bounce back, but it means that something has to change. Now, what that change is, I don't know. So as I pass back the exams, if you have a let's work together on this stamp on the back of your test, it means that I would really like for you to come see me. And let's figure out what it was that caused the grade in the first place. It may be something that I've already changed, but it may not be. It may be the way you tried to study for my course or something like that. But let's figure it out so that hopefully you can bounce back. As you'll see up on the board, these are the grades I have. This is the tests. They were out of 130. Now, when I passed back the exam, when I created the key, I accidentally made it out of 150. So what you're going to see is you're going to see how many points you missed. You would see your grade out of 150, and then I had to go in and do math to make sure it was out of 130, since that's what it says on the syllabus. So you're going to see two grades, one because I accidentally made the key out of 150, and therefore I had to alter it to 130. This is the way it panned out of 130. There were 11 A's, 9 B's, 9 C's, 6 D's, and 11 F's, with one of those 11 F's being for somebody who didn't even show up to the exam. So that gives you a breakdown. Am I happy? No, because this is the easiest test of the semester. Which that really scares me. It scares me for a lot of students because this is the easiest test of the semester. So something, while I did tell those that made a D or an F on this exam to come see me. If you don't like your grade, come see me. Maybe we can figure out a better way to study for my course. And see if we can't get you to bounce back out of the other ranges and up into the A range. So again, I just wanted to clarify how I determined who was at risk and who wasn't. I took into account all grades, but the exam is a huge portion of that. Speaking of grades, I still owe you 2 labs. I am behind on grading labs. I know I still owe you 2 lab grades. Any questions for me? This also does not include, the grades that are reported does not include any of the bonuses you've earned, because I don't use that until the very end of the semester. It actually curves your overall grade, not your individual test grades. Questions for me? I will be posting, I hope to post the answer key today on Blackboard to this exam. Reagan Barrier. Ashlyn Bell. Aiden Bird. Kenzie Blanchard. And remember to come up from this side today since Luna Bear is here. Emma Brown. Jair. Catherine Carter. Christina Charles. Bridget Crimmins. China Cross. Conlon Doss. Peyton Eamon. Alec Fields. This side, please. Karis Foot. David Ginger. Jack Glidewell. Want you to do that, but that's okay. Caitlin Hanson. Layla Harden. Lily Hood. Zoe Hubbs. Landon Humphrey. Regina Johnson. Kylie Jones. Cameron Joyner. Dot Kerr. That is what you said, right?
Yes.
Joe. Not Kinley Key. Rachel King. Wesley Lanius. Tom Mike. Martin Martin. Kyle Payne. Kennedy Pilkington. Tyler Payne. Penny? Is it Penny or Piney? It's Penny. Okay. I wanted to say that and I said no. Yeah. Abby Rain. Tyler Reed. Alexis Reedy. Sophia. Tia Ring. Alejandro Sanchez. Logan Sanders. Brooks Medley. Kinsley Sokos. Savannah Stallings. Ren Ting. Amelia Young. Okay, so just a little bit of more information about the test now that it's been handed back. On the first question, I did not take positive and negative alone. I wanted to know the exact charge, because as we get into cations and anions, they can be a lot more positives and negatives than just a one. Number two, on the periodic tables, if you did not read the question and do as follow the directions, it might have come back to haunt you. Basically, there were questions where I said to give me the elemental symbols primarily, and I got shading. So those were the toughest. The rest of it, I tried to give partial credit where I could give partial credit. So, any questions? Again, I hope to put the answer key up today. Okay, so today we've got a lot to cover, and Thursday we've got a lot to cover. Today we are going to be finishing up, or we're going to discuss electron configurations. I'm going to start by doing a couple more examples. One of them is just to get our brains functioning again over electron configurations that we went over Thursday in the lab lecture. The next one is to talk about electron configurations from the transition metal series. Then we'll get into anomalies. After that, I'm actually going to go to orbitals, and we'll discuss what all these orbitals look like and how they add to the atoms. And we'll talk about nodes. After that, we're going to get into some of the information that's packed into the electron configurations, such as whether it's paramagnetic or diamagnetic, and valence electrons compared to core electrons. And then finally, we'll get into charges of atoms and electron configurations of ions. So going back up, electron configurations of sulfur and quantum numbers. First of all, sulfur is element number 16. So it's going to have 16 electrons. When we deal with an electron configuration, we always start at the top left-hand corner and work our way down. What we find when we start at the top left-hand corner is the one orbital, one shell, S subshell, and hydrogen and helium are in that subshell. Then we move on to the second row, and the first block we come across is the S block. So the 2S, we got to go through lithium and beryllium, so 2s2. We move on over to the 2p block, or the p block specifically, but we're still in the second shell, so it's the 2p block. And there are 6 elements across. We have finished with period 1 and period 2. Now we move on to period 3. And we hit the S block first. And there are 2 electrons, or we got to go through sodium and magnesium, and we're still not to sulfur. Moving all the way across, we then hit the P block. This is specifically the 3p because we're in the third shell. And sulfur is the 4th element in that block. Folks, one way to know if you're on the right track, though it's not a done deal, because you could still mess up in other ways, is if you'll add the superscript. So the sum of the superscripts is equal to 2 plus 2 plus 6 plus 2 plus 6, which is equal to 16, which is how many electrons we said we needed to have. Questions? Now, this is where the noble gas configuration really starts to become handy, because you're starting to get into a significant full electron configuration. If we want to do the noble gas, we find the noble gas preceding sulfur, and that noble gas preceding sulfur is neon. By placing neon in brackets, we're saying that sulfur has everything that neon does. We only need to include what neon doesn't have. So basically, folks, we're saying in our electron configuration, we're going to start here. It's neon, we put it in brackets, and then we go to the 3s2, 3p4. Questions? As far as our box diagram, we have the 1s. It has 2 electrons, one spin up, one spin down. And it only has one orbital, so that's why there's only one line. S only has one orbital. For the 2s, again, S has only one orbital, so one line, and 2 electrons have to go in that orbital. For the P subshell, it has 3 orbitals. So we draw 3 lines. And we place in electrons spin up before pairing until we get to the 6 we said that it had. We do that because P is a degenerate orbital because it has more than, or is a degenerate subshell. It's a degenerate subshell because it has more than one orbital in that subshell. Then you move on to the 3s. S having only one orbital gets only one line, and there are 2 electrons in it. And then you move on to the 3p. P has 3 orbitals, so it'll have 3 lines. And you place one, they are degenerate orbitals. So you place 1 electron in each orbital before pairing until you get to 4. So this would be the box diagram for sulfur. Now, obviously, it would get tedious if I asked for the electrons, all of the electrons. So I'm just asking for the last 2 electrons that were added, which is this one and this one. Yes.
Just to confirm, those are all 1 on the top denominators. The one of them looks a little bit like 4. The one over the 2s.
Oh, yes, that's an arrow.
Oh, okay. Gotcha.
Okay. Now for these last 2 electrons, again, we're always going to, when we write up the quantum numbers, we always do so in this order: N, L, M sub L, and M sub S. N is shown with the number, so that is going to be 3. L is directly dependent upon the letter, and if P means L is equal to 1, M sub L, that is where you have to use your rules. M sub L can be anything from a negative L to a plus L. So for this, that means it can equal a -1 to a +1. So that means that it is equal to -1, 0, and 1. So we can label our lines with -1, 0, and 1. So the last electron added would go into the -1. And then your M sub S is based off of the arrow. And this one being down means that it's a -1/2. That was the last electron we added. The next to last electron we added, the first 2 pieces will be the same. It's a 3, 1. But this time it's in the first orbital. And it is an up arrow, so it is a +1/2. Questions? Okay, let's do the electron configuration for our nickel. You start at the very beginning with the 1s2. Then we're moving down to the second row. Our first block in that second row is the S block, so 2s and 2. Then we move all the way across to the P block. So it's 2p, 6, because it's 6 elements across. Then we move to the third row, and the first block we encounter is the the S block. And it's the second element across. Reading all the way across, we then encounter the P block in the third row. And there's 6. Then we move on to the fourth row, and the first block we encounter is S block. But here is where you have to be conscientious. The numbers preceding the letters throughout this entire electron configuration represents the principal quantum number. But for nickel, since nickel is in the transition metals, remember that the principal quantum number can be determined by taking the period number and subtracting 1. So for nickel, nickel is in the 3Ds. Because it's in period 4, so we need to subtract 1, so that makes it a 3, and it is in the D block. And nickel is the 8th element in that D block. So its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Again, you have to pay attention right here when you get to that D block, because its principal quantum number is 1 less than the period number. Folks, I'm going to be nice. I'm not going to get into the F block. I'm going to stay within the D, S, and P. Now, this is, again, the noble gas configuration is very nice here because it eliminates a lot. So we're going to find the noble gas that came before nickel. The noble gas before nickel is argon. So if I put argon in brackets, I'm going to take care of everything through argon. And I only need to follow along with what's left, which will be the 4s2, 3d8. Now, I'm going to cheat here because I really don't want to do the entire quantum number or box diagram. And I'm going to do a variation of the noble gas and a box diagram combined. So it's argon, 4s. Well, that S is going to be in the, has 1 orbital. And there are 2 electrons. And then we get to the D. D has 5 orbitals. And we place 1 electron in each orbital before pairing. Now for our quantum numbers of the last two electrons added, that is going to be this down electron and this electron that's going down. They are both going to be the 3 for the N because they're in the third shell. They're both going to have a D. Now D means L is equal to 2. So they're both going to be a 2. Now, to get to the next piece, you have to remember that M sub L is equal to a negative L to a plus L. So that's equal to a negative 2 to a plus 2. So it's equal to a negative 2, negative 1, 0, 1, 2. So I'm going to plug those in, negative 2, negative 1, 0, 1, 2. And I find that the first one, or the last one, came into the 0, whereas the next to last one was in the negative 1. And then they are both down arrows. So they're both negative 1/2. Questions? Yes.
Whenever you're writing the quantum number, does it matter if you put the last one first? Or the last one you wrote first, or does it matter?
You always have to put them in order of N, L, M
Yeah,
sub
no, I
L.
get that. I mean,
Oh,
like,
you're
obviously,
talking
this
about
is-
those? It all depends upon how I ask the question.
Okay.
If I say which is the last electron, then that should be the one that you, so if I specify. But if I don't specify, it doesn't, if I just say the last two, it doesn't matter which order. Other questions? So we're gonna see if I can draw this thing and talk about what it means. So we start out with the 1s orbital. And then we add the 2s and the 2p's. In there. Then we add the 3s. And we add the 3p's. Then we add the 4s. And this is where we would come in and add in the 3ds, which is going to get this very, very complicated, as you quickly see. So let's scan down here to see what it would look like. So basically, if I'm just looking at the S's, I'm stacking on the spheres. If I'm looking at the P's, I'm stacking on the P, which is a dumbbell shape, I'm stacking on to it. If I have a D, which is 4 out of 5 of them are cloverleaf, I would just stack on to it. But you can imagine clumping all of that into those diagrams, which I can't even draw properly. So they just build and build and build onto each other. So I want to talk about orbitals real quick before I go back to the anomalies. again, these orbitals. This is the M sub L. But the shape is described by the L value. These orbitals have nodes. And what a node is that it is an area where no electron can exist. The orbitals have nodes. Oh, you're right, sorry. The orbitals have nodes, and the nodes are where no electron can exist. Now, there are two types of nodes that are possible. There are the angular nodes and there are radial nodes. Angular nodes refers to the plane that it passes through, the nucleus. In other words, it is an XYZ coordinate plane. The radial nodes, if you think about it, that includes the word radius, which means it's a circle. And I'll show you how to figure it out, but I'll also show you what it means. So to figure out the number of nodes, the total number of nodes in a particular subshell, the total number of nodes in a particular subshell is going to equal the principal quantum number minus 1. The angular nodes, that again are those nodes that passes through the plane of the nucleus. You can calculate the number of angular nodes because it's equal to whatever the angular momentum quantum number is. Angular nodes, angular momentum quantum number. And then the radial nodes are going to equal, you can look at it from two different directions. One is it's the total nodes minus the angular nodes. So it's equal to n, which is the principal quantum number minus 1, minus the angular quantum number, angular momentum quantum number. Now, to be able to determine the number of nodes, you've got to be able to recognize the orbital and know what n value is the first to have that orbital. So an L of 0 is an S subshell, which is spherical. The first principal quantum number to have an S subshell is 1. The first shell is the first place to have an S subshell. When L is equal to 1, that means it is a P subshell, which is dumbbell in shape. And the first time you see a P subshell is in the second shell. So N is equal to 2. If you have an L equal to two, that means it's a D subshell, and 4 out of 5 of them will be cloverleaf in shape. The other one I've tried to draw here is a dumbbell with a donut. But you don't get any D subshells until the third shell. I'm trying to let everybody have time to write what I've written down. Because now I'm going to work a couple of examples. Okay. So when I see this, let's talk about what I see. First of all, I see an S subshell because it's a spherical subshell. I know that S subshells begin in the first shell. So this is the 1S, this is the 2S, and this is the 3S. So folks, we're dealing with a 3S orbital. My total nodes is equal to n minus 1, or in other words, it's 3 minus 1. So my total nodes is going to equal 2 nodes. For the 3S, my total nodes is equal to 2. My angular nodes. Angular nodes is equal to L. Well, with a spherical shape, S subshell, that means my angular nodes here are equal to 0. There are no angular nodes, meaning there are no nodes other than the nucleus on the XYZ axis. So then you have your radial nodes. And basically that's going to be equal to n minus 1 minus L. So it's equal to 2, 3. It's equal to 3 minus 1 minus 0. So in other words, there are 2 radial nodes. And folks, what those radial nodes are is there is an area right up against the nucleus. If I can figure out how to minimize this. Well, we'll just do it this way. There's an area right up against each one of these nodes, each one of these orbitals, where the electron can't exist. And those are radial nodes because they are circular. let's look at the next one. What I see here is I see a P subshell. P subshells begin in the second shell. So what that means is that this is a 2p and this one is a 3p. So I'm looking at the 3p orbital. My total nodes is equal to n minus 1. So that's equal to 3 minus 1 or 2 nodes. My angular nodes is equal to L. Because this is the P subshell, L is equal to 1, so there is one angular node. And then the radial nodes. That is equal to n minus 1 minus L, or in other words, it's equal to 2 minus 1, no, 3 minus 1. 3 minus 1 minus 1. So it's equal to 1. So what are these? Well, the angular node cuts right here is where the angular node cuts. The radial node is going to be a circle. Again, you can think of radius that cuts right in between them. That's where the radial node exists. Questions? Because you will have this on the homework. You can use the calculations. It doesn't ask you to draw anything. I'm trying to draw it so I can demonstrate it. Yes. That's an angular node. Okay, let's look at this guy. This one's a big one. Okay. First thing I note is I'm dealing with a D subshell because it is cloverleaf in shape. D subshells don't even begin until they get to the third shell. So this is the 3D, 4D, 5D, 6D. So we're talking about the 6D here. If we're talking about the 6D, then the total nodes equals n minus 1, which is equal to 6 minus 1, or 5. So there are 5 nodes in this structure. The angular nodes equals L. Well, L is equal to 2. Those angular nodes, folks, occur right there. The radial nodes equals n minus 1 minus L, so it's equal to 6 minus 1 minus 2, or in other words, there are 3 of them. And those 3, again, you can draw a circle. There's one of them. There's the second one. And there's the third one. Questions about nodes and the atom? Basically, folks, these atoms get complicated quick. I tried back here to start showing you nickel, and it was easy until I got to the 3Ds. And then it quickly gets complicated. And then there's nodes in there where there's no electron inside those atoms. So when we're doing when we developed quantum mechanics, when Schrodinger developed the equation to solve for the quantum mechanics, he is showing you the most likely location for finding the electron. But even in those likely locations, you got to understand that there is areas where the electron cannot go. And that's where the nodes are. And again, and hydrogen was easy, so it's easy to do by hand, the math. But as soon as you get to helium, and especially as soon as you get into lithium and beyond, it becomes so complicated that you really don't want to do it by hand. Because you got nodes that come into play, and you got this, that, and the other that starts to come into play. Okay, for the last little bit, I may not get to everything, so I will tell you, I'm gonna have to go back to my office quickly and adjust the homework. So give me about 10 minutes once class is over to go adjust the homework before you start doing the homework. I was hoping to get a little further than I'm gonna get today. Now, we've developed a process for determining the electron configuration. We go 1, S block, 2, S block, 2, P block, 6, 3, S block, 2, 3, P block, 6, 4, S block, 2, 3, D block, 10, 4, P block, 6, and so on and so forth. But there are anomalies throughout this periodic table. Now, I'm not going to have you memorize all the anomalies because, again, they're scattered. But there are 2 groups that behave as, that every atom in the group behaves as an anomaly. And the 2 groups that every atom in the group behaves as an anomaly is group 6 and group 11. I will expect you to know these anomalies. These two groups, 6 and 11, all behave as an anomaly. Now, how do they behave as an anomaly? Well, for group 6, we're going to promote one electron out of the S subshell into the D subshell. And what that's going to do is it's going to create two half-filled subshells. It's going to create a half-filled S and a half-filled D. And half-filled subshells are particularly stable. Group 11 also promotes one electron from the S subshell into the D. And when group 11 promotes that one electron from the S subshell into the D, it creates a half-filled S and a full D. And half-filled subshells and full subshells are particularly stable. So they create a more stable atom. Let's see it from a box diagram perspective. So chromium, if I were to create the mixture, it would be, whoops, let's get out of the yellow pen. Chromium, if I were to create the box diagram, is argon, 4s, and 3d. Our typical method for filling it would be to put 4s2, 3d, 4. But if we allow chromium to promote its one electron from the S to the D, then you actually get what the electron should be, which is argon 4s1, 3d 5. And what you notice is you have two half-filled subshells, which adds stability. Why does it add stability? Well, this one in particular adds stability because no electron has been paired up, meaning it's lower in energy with all these unpaired electrons in it. For every group 6, you're simply, and what I would suggest on the test is to bring your highlighters and highlight group 6 and group 11. So you remember that those electron configurations are a little bit different. And I did see colors on the last test and I loved it. So go for it, folks. Makes it easier. Copper. We typically fill it and we go argon 4s2, 3d9. But by promoting one of copper's 4s electrons into the D subshell, you get what you really should have, which is argon 4s1, 3D 10. So you have one half full and one filled subshell, which provides stability. This is going to be what happens to every single element in group 11. It's going to promote one from the S into the D. So these I've done on the left-hand side are incorrect. They would give you no points because electron configurations are either right or they are wrong, folks. There's no partial credit. You're warned now, there's no partial credit with electron configurations. They're either right or they are wrong. Questions? Okay, so let's talk about information that's packed into these electron configurations. The first one we're going to talk about is paramagnetic or diamagnetic. Basically, will the element be attracted to a magnet? If it's paramagnetic, it will be attracted to a magnet. Where if it's diamagnetic, it will not. So how can you tell from the electron configurations? Paramagnetic is going to have electrons that are not paired up. In other words, they're going to have one or more electrons that is a plus 1/2 without a negative 1/2 beside it. Whereas diamagnetic is going to have them all paired. There's also something called ferromagnetic, which I'm not going to worry about. All I really am going to worry about is para and dia. So we look at the electron configurations that I have written with nitrogen. Nitrogen has 3 unpaired electrons. So it's paramagnetic. Argon has 0 unpaired electrons. So it is diamagnetic. Fluorine has 1 unpaired electron. So it is paramagnetic. Now admittedly, fluorine is less paramagnetic than is nitrogen because it has fewer unpaired electrons. Questions about para and dia? Once if you can get electron configurations, and you can do the box diagram, getting para and dia is easy. And all you're looking for is, does it have any unpaired electrons or not? The hard part here is writing the electron configuration in the first place, specifically the box diagram. I think this is a good place to stop because I'm looking out at faces and you're looking, not that a tired eyes is gonna change on Thursday, but you're looking tired. And therefore, I don't think anything's going in. Stay. If people want to pet you, that's fine, but you gotta stay. Huh? Yeah. And if you did not sign in because you walked in late, the sign-in sheet's here. Remember, this is how I'm determining points per day. You gotta come sign in. I don't need your test back.
You said you didn't need like just positive or negative.
It needs to be a +1 or -1.
Okay.
No, I need +1 or -1 because that way it's differentiating it from having too high of a charge. Yes, I will do that. And I also have your test if you came in late, so.
I understand mostly everything. These subscripts, the superscripts, sorry, in these.
That's the number of electrons in that particular subshell. So if you count across, you'll find out the S block can only hold 2.
I feel the same.
And then the P block over 13 through 18 only has 6.
For the first one,
Hydrogen, helium belongs over there in the S block. It's the opposite.
how many electrons is helium?
2.
So would that make 3?
So, oh no, each element has, so helium only has 2 electrons,
Right.
period.
Yes.
So it would have hydrogen and it would have, hydrogen only has 1, and then you add 1 more electron, you would be helium electrons. So in other words, it's not additive. for number of electrons. It's
Okay,
how many elements did you go? 1, 2, helium's 2.
okay. That makes sense.
A couple of careless mistakes on the Ed puzzle. Is there any way I could like?
I didn't let somebody else the other time do
Okay,
it. Keep in mind, I dropped one,
Okay.
so
Lily asked if I could pick up the test.
I will not allow people to pick up tests for other
I didn't.
people.
Do we need to give the test back?
No,
I know that this is kind of like far out, but I wanted to ask you because, my brother, he's going to nationals for, FFA, like, Arkansas. And it's in November, but it's whenever we have exam 3, November 2nd, I would be gone, and I didn't know if I was allowed to do like a makeup exam after.
you would have to do it before.
Before? Would it be like that Tuesday before, since it's on Thursday?
November 2nd.
Or I
That would
guess,
be the
that would be
Wednesday.
Halloween.
You would do it the Wednesday before or something.
Okay. I'll leave that Tuesday,
You leave
if I
Tuesday.
were to.
What time?
I'm not sure just yet.
We'll have to work it closer to time to figure
Okay.
out exactly when you can do it.
Okay.
Oh, I wanted to ask one of your office hours.
Best thing to do is look at Blackboard. I know I have an office hour, I think at 11. And one at noon, and no, I'm gonna be in my office from noon to 1. And then I'm gonna be in the office hours from 2:30 to 3:30. No, I don't.
Let me see if I have one.